Hello, everybody. We are talking about Chapter 1 tonight. I'm going to be going through the PowerPoint slides that come with Chapter 1. They're attached to the topic list at the top of the unit folder. And this is a pattern that you guys hopefully will get used to. This is really the first real, content unit for us in this course. And you can see that the topic for the unit is Introduction to Problem Solving. We will be focusing on Chapter 1 in your book. So if you're looking for what you need to read, Chapter 1 is what you need to read. For some people, it's adequate for them to just go through the PowerPoints, but the book does have significantly more detail and example problems that I think are very helpful. The guy writes the stuff pretty well. And typically what I'll do at the top of every unit folder is I will provide any supporting documents and PowerPoints with the topic list and kind of a brief listing of what we will talk about in that unit. Another thing that you're going to see as you scroll down is the fact that there will be videos available. And I'm trying to find my archive videos here, which apparently didn't copy over to the online group. Sorry, online people. I will fix that for you. But I do provide videos, and you notice I'm still recording them right now, so that's why they're not out there yet. But what I typically do is the day after class, I will take the videos, render them, push them up to YouTube, and then provide a link in the course shell with a description for each video. And that way, if you weren't here, or even if you were here and you thought you missed something, you can go back to the video and watch. It becomes more useful as we actually dig into the material and we're writing code, and you can watch me solve a problem, see the solution to something. Okay, so I think that you'll find that quite useful. Onliners really enjoy that. On occasion, and that's what I'm looking for right now, and I'm not seeing it, so I must not have turned it to visible. So I'm going to go into my edit mode here, and there they are. Notice I have my old videos are out there. So videos that I put, now these are not on YouTube, these are off Gateway servers, but I have my archive videos that I'll release to you guys just for right now to get started. If you really want to go home tonight and first thing you want to do is watch my videos, which I'm sure that's going to be the case. Okay. But this is kind of what you'll see. You'll see just a link, the length of the video, and a brief description of what's in each one. And as the course proceeds, we'll have quite a little library of them that you can always refer back to. And since the new ones will all push up to YouTube, the lecture videos will remain. Homework videos will be occasionally turned off and on depending on what point in the semester I'm in. All right. So I'm going to go ahead and dig into the PowerPoint, folks. And let's get started. All right, so we're looking at Chapter 1. 3 different sections in Chapter 1, and these are the ones that you see. So we're going to look at some background on how programming works, basically, on a rudimentary level. We'll talk about how the procedures work for creating programs. There's actually a technique for it. It's all built on systems concepts, and we'll talk about that. And then we'll also look at the tools that we'll be using. Now, initially, the first thing that we're going to do is we're going to learn that the most important part of writing a computer program is figuring out why the heck you're writing a computer program. As silly as that sounds, right? Why are you going to school? Oh, nothing better to do. No, you're going to school for a reason. I'm hoping that reason is to become an IT professional, right? It really is a great career path. Right now, if you look at the job data that's out there, there are so many open positions, even in this area, that are looking for qualified, trained computer programmers, web programmers. They cannot fill the positions. So what do? Remember when Trump was in Kenosha like a couple of weeks ago? Why was he here? Because he wants to fund schools to train people so we don't bring in people from overseas to take our jobs, right? Isn't that interesting? So we have this, like, these programs where we bring in people from overseas who are qualified to take the jobs that we could be taking ourselves. So it's really a great field to get into. The opportunities are great. You can make decent money, and it's fun, frankly. All right, let's talk about some of the real rudimentary things. Many years ago, when I started studying IT, I had a teacher, that kind of resonated with me. And it was a she, and she said, computers are just dumb machines. They can't do a damn thing on their own. All they can do is exactly what we tell them. Now, if only I could get my children to do that, then we'd have something going, right? but it's very true. Now, computers themselves, they really, when they operate, they don't operate like our brains operate. They're digital devices. They operate with electricity, and electricity basically has a capability of sending positive and negative voltages. Some people think of it as on and off, but it's really positive and negative voltages that, in combination, a whole series of positive and negative voltages expressed a certain way might translate to be a letter or a word or a programming statement or whatever. That's how computers operate. That information, as it's traveling through a computer system, as what we would conceive as a series of digital ones and zeros or electronic pulses, that is machine language, the lowest level of communication that the machine understands. Well, actually what the machine understands. It really doesn't understand anything beyond that. It's just those positive and negative voltage pulses that it understands. Humans, unfortunately, don't communicate that way, right? We use words, we have nuances in what we say, we have sentences, we have languages, and we're here to basically not only learn a language, but we're also here to learn a technique for writing software. So because we can't speak like computers do, what they've done over time is they've developed what we call high-level computer languages, which take things that are kind of English-like and converts it ultimately somewhere in the background to that machine language that the computer can actually run and execute. So that's what we're here to do. Now, whenever you write a computer program, in fact, whenever you're really kind of doing anything, actually, and you might not even realize it, it's a process of solving a problem and the steps involved in solving that problem. And you might not think about the things that you do on a daily basis in this fashion, but this is what computer programmers do. For example, when I came into class today, I was carrying 2 computer bags, and then I had this big box of books. And I'm like, oh, okay, let's see. I gotta put one bag on one shoulder, one bag on the other shoulder. Dang, this is really heavy. I can't carry this all at once, right? All right, so I'm gonna break this down. I take 2 computers out, take them to my office, and I'll come back to the car and I'll get the books, right? So I took this task of taking the stuff from the car to the office, and I broke it down and I said, well, we're gonna do the books separately. We'll do a separate procedure, so if you will, to go get the books. But you know what? The books weren't even that easy, because the books are in 3 different boxes, and I'm like, I'm not gonna carry 3 boxes. I think I can get them all fit in one. I took the books out of the other 2 boxes, gathered them together, and put them in one box. So really, what I'm doing intuitively as a human being is I'm looking at my situation for what I want to accomplish. So I'm understanding the problem is get those books up to the office, and then I'm taking that problem and I'm breaking it down into little pieces and steps that I can tackle. You know what? Because any problem, if you break it down into enough small little pieces and just start tackling each little piece one at a time and crossing it off your list, pretty soon the problem's done. That's how computer programming works. Understanding the problem, breaking it down into pieces and solving each piece separately. Now, programming can be done in a number of different ways. One way is by having basically kind of a sequence. You can see a program is a sequence of instructions. First, I step out of the car. Next, I open the back door. Then I reach in and grab the books. You know, it's a step-by-step thing. And the biggest challenge for people that are new to programming is to break down the problems that you're trying to solve into granular little step-by-step pieces. And that's where we start in this course. So we learn by pseudocoding first, and then we write code around it. Notice what it says here. Programs can consist of only a few instructions or millions of lines of instructions. That's kind of mind-boggling, really. Can you imagine all the code that just runs Microsoft Windows? All the little different things that happen inside there? And we take it all for granted. After this course, you won't take it for granted. All right, so here's got a slide that says all programs have in common. It says you take data and you manipulate it to produce a result. This is true. But there's a process to manipulating that data. And notice that the second bullet starts to break that process down. You notice they got input, process, and output. And then what I always think about, because I know that when I learned this, you know, I don't know if they even broke it down into these steps succinctly, but it certainly was very similar to this. And if you think about it, when you sit down in front of a computer screen, you're presented with a screen, right? And what happens? Well, usually nothing happens until you do something, right? And that part of it is the input. So you might be sitting on a web page and there's a form, and the form might just be to log into a site, let's say, for example. So it's looking for some input. What input is it looking for? A username, password, right? So the input would be your username, hopefully the correct password. And then you click log in or submit or whatever you hit, and then something's happening in the background that somebody programmed. And basically what it's doing is it's going, do we have that user? Is that the right password? He's good. Or, right, it's going to go, not good. And then maybe you only give them like 3 tries or 10 tries and you lock them out. Or maybe you give them an option to reset a password or something like that. But there's a process that happens in the background. And then whether you are successful or you fail, there's some sort of a message that comes out on the screen, which is your output. So there's an input, there's something that happens in the background, and then there's an output to indicate that something happened. And that output could just be something on the screen. It could be to output to a file, write to a database. It could be a number of different things. All right, you guys know what a computer is? Gosh, I hope. Right? Computers don't do anything until we put software on them. Microsoft Windows, or the Mac OS, or if you run Linux, or if you have a Raspberry Pi, or if you have a phone, this is a computer too, right? What operating system do I have? Android or iOS, right, if it's an Apple device. There's others. Windows has phones too. I don't think anybody owns any, but all of them share these types of things. We have some sort of way to see what we're doing. There's some sort of a processing unit inside. There's a chip inside there that does all the processing of the machine code, reads and writes to drives and whatnot. But the part that we're interested in is the software. That is the instruction set based upon the solution to the problem that we came up with. So we will figure out what that problem is. We will figure out step by step how to solve that problem. We turn that into computer code. We feed it into the computer, and then the computer does it for us. The beauty of writing a computer program, of course, is once you've created it, it can be replicated. And if we try to do something better, we can take what we've already done and make it even better. That's the beauty of it. It's a whole lot better than digging holes for a living. All right, remember I said I started with counting at 0? Computers always start counting at 0. You want to know the why for that? And since I'm kind of like in edit mode here, right? We have a base 10 number system. And we usually use counting numbers. We go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what do? 10, but that's 2 digits. But it's a base 10 number system. The 10th digit is 0. So computers always start with 0. And then when you get to the numbers that follow, when you get to 10, then you start using 2 digits. They always start counting at 0. That becomes important when we get to the point of working with certain data structures, like arrays, for example, or lists, where the first item is position 0, not 1. Our brains think 1, the computer thinks 0. That's kind of interesting. You guys are programmers, right? Notice what programmers do? They solve the problem and write the instructions. People who use your software, they're called users. End users in some cases. We're working with lots of different versions of Windows. Depending on which version of Windows, when we start to create programs in this class, we will be creating graphical programs. So in other words, we'll be creating applications that run inside of Windows as a window. Now, in some of the other classes that we teach in our programs, whether it's on an IBM platform or PC, or you learn Java or Ruby or any of these other weird languages, sometimes we write programs that are on a console. You guys know what a console is? It looks like this. You know, where it's just like text on the screen, that kind of thing. That's a console. So another way to write programs is to write programs that just give you text output. This is old school. That's what I learned. I always joke with students, when I learned to write Windows programs, first I had to spend like a couple of days writing the windows just to create the windows, and then I would write the code to make the program work. You guys will be working with Visual Studio. You want a window? You just draw one. You want a button? You just drop it in. But then you still have to write the code to make it do something. So that's the one advantage you're going to have in that environment, which I think is a lot of fun. And I'm hoping that we get to be doing that tonight before we leave, depending on how much I talk. We'll see. All right. There is a process to writing programs, which hopefully you're catching on to. And a lot of it really comes down to the planning and understanding. And some experienced programmers have the capability of first going directly to the code. I'm going to tell you what, when you start to write programs that are more complicated than the things that we do in this class, where it's like a real application that does a whole lot of different things, there is no way you can just jump in and code. And that's why you learn pseudocoding and all the logic first. It is critical to being successful, especially as the complexity grows. So let's look at some of the terminology they have here. Projects and applications and solutions. And these are kind of terms that we're going to throw around, kind of, you know, they're kind of synonymous in a sense. Really, whenever we're creating a piece of software or a program, it really is an application. An application really is a programming project, and it's also in Visual Studio often called a solution. And a solution really just refers to kind of a collection of different programming resources. So you might have one file, or you might have many files, and all of those are part of one solution or one application or one project. That's the meaning of this slide. So what is software? Well, basically software is a set of instructions. But it's a set of instructions that's been converted from the way we understand a programming language that's kind of English-like, converted to those ones and zeros the computer understands. Notice what it says. Hey, the computer only knows how to do what the programmer tells it to do. Otherwise, it's just a dumb machine. It's no smarter than your lawnmower. Well, maybe a little smarter, not much. All right. Basic process of creating a program. Notice what it says here. It says, performing a task on the computer. You determine the output. For example, I went to that website. I want to log in. I've determined that the output I want to see is that you've logged in successfully. Identify the input. Well, how do I log in successfully? Well, with my username and password, I hope. And then it says determine the process necessary to turn that input into the desired output. Now, we don't give that a second thought, do we? Right? You go to any application, you log in. You really don't give it any thought. It just kind of happens. But you know, there's a logic behind it. And different websites will log in different ways. Different pieces of software will operate different ways because whoever designed that program thought that was best. So think about like all the different pieces of software or websites that you need to log into and how all their login processes are completely different, right? You go to log into your bank website, chances are you got like a multi-factor authentication. They probably have some security image, and then you got to like put your login on one page, hit a button, go to a second page. Sometimes they ask you like what high school you went to or what's your favorite food, right? Somebody's got to program all that stuff, right? And why would a bank be more secure, right? Well, you don't want people taking your money. All right. Unfortunately, folks, programming often involves math or a component of math that people often don't think about, which is just logic. And logic really is, you know, not something you should be afraid of. And I know a lot of people freak out when they get to the math components, right? Well, all of you have to take math classes to graduate, obviously. People usually hate them. But computer science and mathematics go hand in hand. In order for me to get to like my master's degree, I had to do like 3 courses of calculus. I have so many graduate credits in mathematics. I can teach math if I wanted to. You know, that's how much you get. But the thing that's interesting about math is math has a process also, because you're presented with a problem, and the way you solve the problem is you don't just come out with the answer, right? Like if you're given an equation and you say solve it, it's like, I don't know the answer. Of course you don't, right? You got to take it and break it down into pieces. And like you might have to do a little simplification, a little like, you know, divide on both sides or multiply on both sides or canceling things out, and all of a sudden you'll have the answer. But there's a process and technique for it that is completely learnable, predictable, and repeatable. So if you guys do get to the point where you guys are in like math classes and you're freaking out to it, math is one of the best sciences. You know why? Because it doesn't change. Computer science changes all the time. It really does. It really changes fast. So for you have a little example here. It says problem solving. How fast is a car traveling if it goes 50 miles in 2 hours? Okay. Right. That's not too freaky, is it? No, that's not too freaky. All right. So what they're trying to show you here is that here's your problem, it's stated, and then what are you looking for as a desired output? Well, I'm looking at how fast I'm going, right? So what number would I need to put in to get that information? Well, I need to know how far I went and how long I went, right? So if I went 100 miles in 2 hours, I'm going 50 miles an hour, right? And you'll see that once you have a solution created for some sort of a programming problem and you've designed it well, then that solution can apply to any situation, right? Then you can put any distance or speed in there you want, or time or whatever, and it will calculate correctly because the solution is correct. Notice at the bottom, the way you get to the answer with the process, there is a little bit of math. How do we get that speed? By just doing some simple division. terms of a graphic, input, processing, and output, you will write your programs in that fashion. Like you probably put a screen up that says, enter your distance, enter your speed, or time, or whatever. And then you hit the button, and it does that math in the background. Then you have a different spot where you're going to put the answer on the screen. And that's really kind of it in a nutshell. It's not really that much more complicated. If you have more complicated problems that require more complicated math, like think about like if you are online, let's say trying to calculate a mortgage, well, there's a few more things you would type into that equation, right? How long your mortgage is, how much the house costs, what's your interest rate, how much money down, that kind of thing. So there's 4 inputs. But you know what? That's not really that much more complicated either. So it's all about breaking it down into pieces. Now, I always like this paradigm for explaining how the process of programming works. Recipes are a perfect example of a programming problem, right? I desire a chocolate chip cookie, right? That's my desired output. A delicious homemade chocolate chip cookie. Right? So what are my inputs? The ingredients, right? Need some brown sugar, some flour, some chocolate chips, some butter, maybe a little baking soda, pinch of salt, nuts, if you want to, whatever. Lots and lots of butter, more than you ever think you should put in a cookie. And then the process is you take those inputs, mix them together, form them into little shapes, stick them in the oven for a certain amount of time, and a little bell goes off and says you're done, and out come the cookies. So you see how like a recipe is really very much like a programming problem. It's a nice analogy for how we solve a programming problem. So that's a good one to keep in mind. And notice here, I like the first bullet on this one. It says, always have a plan before trying to write a program. You do not jump straight into the code. You guys, I'll be frank. Some of you will be able to, when we get to writing the code, you'll just jump right in and do it, and it's not a big deal. But when we teach you how to pseudocode at first, it's for a reason. Because you'll get to some of your other programming classes, especially web and software people, where I'll have like end of semester projects. There's no way you can write the program unless you pseudocode it first. It's just impossible. Because it's really like writing 20 small programs. And there's no way you can even conceptualize it unless you sketch it out somehow. Same thing is true for building websites and other things like that. There is actually a procedure for doing these things. It's called the Systems Development Lifecycle. It's kind of spread over the next 2 slides. And depending on what resource you look at, some people say there's 5 steps, some people say 7, some 8, some 6. But they really kind of boil down to the ones that you see here. And the ones that they're pointing out really are focused more on application development on these slides. So you'll see the first thing is take a look at what you're trying to do, analyze it, right? Heard people have jobs called system analysts. That's what they do. They analyze problems that need to be programmed, and in some cases actually code them. But you have to like know what you're trying to do. So I'm trying to bake a cookie. That's my definition, right? That's my problem. And then you design it. So in other words, you figure out how you're going to do it. So, well, I got to get my ingredients. I got to get all my bowls and spoons and mixers, and my oven's all ready and all that stuff. And then choosing an interface. So for example, when you're writing a program, I showed you what a console output looks like an old DOS window where it's just text. But I already told you that in this class, we're going to be writing stuff that goes directly into a graphical window. So we'll have a window. We can change the shape of it, the color of it, the size of the text, move things around. That's all it is. And you can get creative with it if you want. Then once you have that interface put together, the next thing you do is you code it. You take the logic that you figured out in your pseudocode, and you write that into the actual application itself. Once you've written it, then guess what you do? You test it. You check to see if it's working. hopefully it's perfect, right? I'm going to tell you what, in programming, it's rarely how it goes. Rarely will you write something and it'll be perfect the first time you try it. There's always going to be little hiccups. Oh, I forgot to do this, or hey, I should have done that, or it should have been this instead. But that's part of the testing and the debugging. And that is part of, helping kind of to help you like make sure your logic is right. If you pseudocode properly, hopefully your logic issues and your math will already be solved. So for example, if you write a computer program that is a mortgage calculator, you better make sure the calculations are correct, especially if like your business enterprise actually relies on it. And then finally, and some programmers consider this optional, is you document what you did. Now, I don't enforce a lot of documentation in this class. There will be times where I will, and there will be times where I won't. It will depend on the project that we're working on, but it's considered best practice after you write a piece of software that you have instructions for how it works, either for the person that's going to be fixing the program after you're gone, or for the user that's using the program so they know how to use it. All right, these are some of the programming tools that we're going to talk about. And the ones that we're going to focus on mostly in this class are going to be the flowcharts and the pseudocode, but I will show you the hierarchy charts as well. Have you guys ever done flowcharting before? Do you know what a flowchart looks like? It's like little boxes and arrows, right? And squares and trapezoids and diamonds and circles and things like that. The reason programmers often use flowcharts is because it creates a picture. And you know what? When it comes to doing something step by step, a picture is a pretty useful thing. It really is. Whether you think that way or not, for some people, when they do the pseudocoding part, or the problem-solving part of the programming problem, the graphical part of it is what totally makes sense to them. For other people, it will be the pseudocode, which would just be the list, the written list of the steps. And that's what you see here. And then the hierarchy chart, which, generally speaking, I think is more of a little bit more of an advanced technique, is a process where it's kind of graphical that shows the interrelation between the components of the program. Because sometimes programs don't always follow a linear step-by-step. Sometimes they're kind of all over the place. So that helps you to identify that. Here's a word you'll want to know. Somebody say that word for me. Algorithm. And an algorithm really is exactly as it says. It's really a listing or a description of step-by-step instructions for solving a problem. So if you ever hear anybody saying, oh, hey, what's the algorithm for completing that problem? Any mathematical problem that you try to solve will have an algorithm for solving it. Computer programs have to have an algorithm. Very often, you're going to see that in computer programming, a lot of the algorithms, the basic ones, people have developed for decades already. So very often, you don't need to reinvent the wheel. That's one of the benefits of being a programmer these days. I mean, we'll learn the rudiments, but when you go out into the field, you're not probably going to sit down and write a password prompt program because somebody's already done it. Unless you came up with a clever new way to do it, chances are you wouldn't even bother spending the time to do it because somebody's already done it. You'll just get the problem solved that you need. All right, let's kind of do a little bit of an example of some problem solving. All right, how many stamps do you need to put on a letter? Oh yeah, it says right there, it says one. They got a rule here, right? It says, rule of thumb is to use one stamp for every 5 sheets of paper or fraction thereof. Okay. The truth is, if you're sending it, like in the U.S. mail, one stamp is for a 1 ounce envelope, right? So you can have a letter, whatever's inside of it, as long as it's flat, up to an ounce, you can send for 1 stamp. All right. So, but they're giving you a different thing here. It says 1 stamp for every 5 sheets of paper, and I think that's about right. So there's an algorithm for it, okay? So if I want to figure out how many stamps I need, well, how many papers am I sending? So you ask for the input, right? Divide it by 5. So if I say I'm sending 10 pieces of paper, I divide by 5, and it will tell me I need 2 stamps, right? Well, what if I only send 8 pieces of paper? 2 stamps, right? But all of a sudden, there's like a logic that goes there. That's like, well, if it's 5 or less, it's 1. If it's 5 or more, up to 10. So you got to come up with the math. And really, it's a divide by 5 thing, isn't it? So it says divide by 5, round the quotient up to the next highest whole number. What's a quotient? Louder? Okay. The answer for a division problem. So if I divide 8 by 5, the answer is 1 point something, right? So you don't even have to worry about what the math actually is, just as long as you know it's not 2. If it's higher than 1, or if there's a remainder, you know you need 2. All right, simple as that. All right, so that was kind of a pseudocode way to do it, verbal description. Now we start talking about the flowchart. What's kind of fun about flowcharts, it's really kind of a whole school of study, honestly. Flowcharts, because they're graphical, I think, especially for beginning programmers, are very, very handy. Because you can see where you're going from and to. And then when you get to a spot where you might have to make a decision and branch off, you can visually see it and you can trace it down and figure out where you're going. So it's kind of neat in that capacity. So here's some of the basic shapes. All right, so you have the flow line, so you're going to have like these arrows. It just shows what step to another you're going, which object to another. All right, and then you have like these ones with the rounded corners. And notice that's for beginning and end. Ones that are trapezoid, in other words, boxes that are sideways. Tilted like a box that's italicized, if you want to think of it that way. That's where we do our input and output statements. So if we ask the user to enter their username or enter the amount of pieces of paper they're using. And then the processing, which is something the user does not see or interact with, that just goes in a square box. That's where you put like your math, that kind of thing. If you get to the point where you need to branch off and make a decision, is it more than 5 or less than 10? And then you would follow a path. You'll see these as we work. And then there's a couple of other little things here, connectors and annotations. And basically, just to summarize, an annotation really is just a verbal description of what you're doing. And what I'm going to do here, folks, is I'm going to show you this flowchart here for the problem that we just discussed. And then we're going to take a break, just in case you're wondering. So take a look at how this one lays out. At the very top and the very bottom, we have kind of those rectangles with the rounded corners. And all they say is start and end. Start the program, end the program. That is required for all flowcharts. So any of the flowcharting assignments that you guys will do, they'll have to have those shapes in there. All right. Then we move on to the next step. And it says obtain sheets. Now this, because of its trapezoid shape, the one that's tilted sideways, that indicates that it's an input statement. And what I'm going to instruct you to do is maybe even be a little bit more verbose. So I might say, I might put in there, get number of sheets from user, or ask user for number of pieces of paper. And then you can see we have two boxes that are just regular old rectangles, and these are processing steps. And what will happen here is we're going to say set stamps equal to the number of sheets of paper divided by 5. And then in a separate steps, we're going to round the number of stamps up to a whole number. And then we maintain that information. And then once we've figured out what that whole number is, then we'll go back to the trapezoid shape, which is in this case going to be for output, showing it to the user how many stamps they need. And then the program is done. On the side, they have the annotations. If you want to annotate your flowcharts, feel free. I will let you know when you need to do them. Typically, I really don't care too much. Because if you fill these in correctly and in an explanatory kind of way, it won't be necessary for you to really annotate as much. All right, I'm going to pause the video here. We'll take a short break and we'll come back. So the key to pseudocoding really is that you're using phrases that are sort of the way that you would talk the problem through and kind of combine it a little bit with the programming language that you're manipulating. So for example, you might actually declare variable names or certain procedural names or function names or things like that right inside of your code. But that doesn't mean anything to you yet, don't worry. It will soon. Okay. So don't worry about that part of it. The other approach, one that we really don't spend a lot of time teaching here, is a hierarchy chart. And as I was mentioning before, it really kind of shows more how the program fits together in pieces as opposed to showing how the information actually flows. So the point here is that, all right, so there's a postage stamp program. That's the hierarchy, right? That's what we have. And what do we do with that? Well, we get some input. We do some output. Here's the processing. The processing actually breaks down into several steps. And this is a simple problem. If you got to one that was really complicated, this hierarchy chart could be huge, right? This is not one you have to worry about for tests or assignments. Yay. All right, I mentioned this to you earlier. How do you solve a big problem? One step at a time, right? How do you build a house? You don't snap your fingers and have it appear, right? First you pour the foundation, then you build some walls, and you put up some drywall. There's a process. Each one is its own step, basically. All right. There are 3 main techniques that you can use to solve any logical and programming problem. And they break down to these 3 things. Sequence, and that's what we've looked at so far, right? Where we do things in a particular order. First you do this, then you do this, then you're done. The second type is what we call a decision. And that's where you get to the point, and it's like, you might be a simple question. Did the user put in the right password? If they did, you let them in. If they didn't, ask again. So you actually branch at that point. So depending on what's happening, that's the course of action you take. So that's a decision. And then the last one is what we call looping. Sometimes we call it repetition. And that is sometimes when you do certain things to solve a problem, the process is repetitive, right? So for example, if I am building that house and I'm nailing up or screwing drywall up to the wall, what's the process? Well, I take a sheet of drywall, I hold it up against the wall, and I put screws in it. Then I get another sheet of drywall, put it up against the wall, and I put screws in it. And I just keep going until I can't do that anymore, right? So that's a repetition. So the thought is, in terms of this type of information science, basically, is that any programming problem can be solved using these 3 structures. Some people will refer to decision as selection. So if you ever hear sequence, selection, and repetition, but this author uses the words sequence, decision, and looping. I may often refer to them interchangeably, and I'll try to make sure that you understand which I'm talking about. Step by step, in order, there's a decision that needs to be made, or there's some sort of repetition that happens. A sequence, well, that's a simple step by step. We've seen that already. But if you get to the point where you need to make a choice first, then you will start to flowchart in this fashion. So for example, we check to see, is the condition true? If it is, we perform one action. If it isn't, we perform a different action. That will be a few chapters down. So here they have an example. It says, given a street number of a one-way street in New York City, decide the direction of the street, either eastbound or westbound. Yeah, did you guys know that in New York City? The numbered streets in Manhattan, if they're, well, I forget which. The even numbered streets go eastbound one way, and the odd numbered streets go westbound. People that live in Manhattan know that. So when they drive around, they know they have to go like 2 blocks down before they can turn a certain direction again. It's kind of odd. You're going to flow chart that. Here's what it might look like. And this is how a decision works. You figure out which street you're on. I'm on 47th Street. So which way does that go? Do I have to look back? Is the street even? No. So we go westbound. That's all there is to decisions. Okay. That's in a nutshell. We will be looking at that in pseudocode too. In pseudocode, this is where we start to actually, this starts to look a little bit more like programming code. It's not exactly code, but you can see when I'm doing pseudocode, I might say, if a street's even, then we go eastbound. Otherwise, or else, you go the other direction. So it's starting to look a little bit more like code. Here it is in a hierarchy chart. Once again, I'm not worried about you guys studying that, so don't worry about it. We get to the other structure, looping. The perfect example for a loop, for me, is I always think of like logging in and putting in the right password or the wrong password, right? You put in the wrong password, you ask again. You might put a message up that says, what, are you an idiot or something? Or did you forget? Or your cap box is on, or something like that. But then if they finally get it right, you can move along. Now, this next little problem, and I know I'm going through these quickly, but there's no assignments based on these yet. This is kind of an overview of what's to come with these last few slides. They talk about a problem that says calculate and report the average grade for a class. All right, well, how do you do that? Well, first I have to get all your grades. I have to add them up, and then I have to divide by the number of students there are. Right, that's the procedure. So what do I need as an input? I need all your grades. And how many of these there are, obviously. And then the processing is you do the math, find the sum of the grades, count the number of students, and calculate the average. And then finally, the output's going to be to display it on the screen. All right. As a flowchart, notice it gets a little bit more complicated because here we have all the data structures, all the different techniques. We have step by step, we have decisions, and we have looping. Because here's what happens. If I'm going to get your grade, all right, Sherry, what's your grade? 100. Javier, what's your grade? Do you see a repetition happening? That's why there's a loop here. So we get the grade, it's a repeating process. And then every time I do that, not only do I get the grade, store it, and add it to the total, I'm also going 1, 2, 3, 4, and all that stuff happens repetitively. But even in that loop, it's kind of a series of incremental steps. Don't worry about the details of how this works right now. We will get to the chapters where we'll put all these structures together. We're going to start with really simple ones like the paper one. Okay, that's where we're going to start. Notice that the flowchart also can become pseudocode. And they use words like loop for this part, which is a loop. Once again, the hierarchy chart we're going to jump over. And then we are at the bottom of the PowerPoint, thank goodness. Right? It's almost over. Right? They have a couple of comments here. So it says you get start at the top, follow it down to the bottom. I guess that makes sense. Before you start to code, and I'm telling you right now, this one will be on one of your tests. So asterisk here. Don't say you never heard of desk checking, but the process of pseudocoding and flowcharting, and then just checking if your logic works before you even code it, that process is called desk checking. And programmers do use that predominantly to make sure that their logic is right and their math is right. Right? You don't want to put a formula into a program that doesn't give you the right numbers. It's pretty useless in that situation. That process is called desk checking. All right. Tips and tricks. Yes, flowcharts are kind of a pain. The pain about flowcharts is that last part of it where it says difficult to update. Because if you create a flowchart, and I will show you just here in a little bit how to do that, it's a graphical process. So if like I want to add something to the steps, guess what I have to do? I got to move all the others. Right? That's kind of a pain. And you got to move all your arrows and boxes and words and all that. There are some tricks to help it go a little bit easier, though, which I'll show you. A lot of programmers really do favor pseudocode. I am one of them. Some of them, hierarchy charts, I really don't see a lot of people using hierarchy charts out in the field, but maybe I haven't worked at those places. So, but pseudocode is really a good way to do it because you can write out verbal descriptions, and then you can start to kind of take the stuff that you're writing out in verbal descriptions and kind of write it in a way where it is code. So in some cases, you can even take your pseudocode and dump it right into the coding platform and convert it to code pretty easily, especially if you do it right. All right. I'm not going to deny, though, that the picturesque components of working with flowcharts are pretty important because when you can see it, for most people, it resonates more. It's not true for everybody. In the web program, when we do our orientation class, and none of you guys are web people, but some of my onliners might be, we do spend a little bit of time talking about that in terms of like what kind of learning style you favor. Like with some people, if they see a picture of something, they get it, right? Some people, they need to hear it. Some people need to write it out. It just depends on your learning style. And knowing what your learning style is kind of part of this process. So you might work with the flowcharts and go, this really works for me. I get it. It resonates. This is my way, and that's the way you'll do it. For me, pseudocoding is the thing. But on occasion, I will kind of combine them in crude fashions too. There's really no rule if you get out into the field unless you're trying pseudocode just to make sure that things are going the right way. So that's just my 2 cents worth. All right, folks, that ends this PowerPoint presentation. And we'll see you in the next one.